Hello students, and welcome to section 4-4, Proving Triangles Congruent. SSS, which stands for side, 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 and SAS, which stands for side, angle, side. So the side, side, side postulate. You know that two triangles are congruent if corresponding sides are congruent and corresponding angles are congruent. The side, side, side or SSS postulate lets you show that two triangles are congruent if you know only that the sides of one triangle are congruent to the sides of the second triangle, which is what it states. If three sides of one triangle are congruent to three sides of a second, then the triangles are congruent. In the example, it says write a two-column proof. Given that AB is congruent to DB, which you see in the picture, AB is congruent to DB, and C is the midpoint of AD, prove that triangle ABC is congruent to triangle DBC. Okay, so what we're going to go ahead and do is we're going to mark our picture such that because we have a midpoint of C for segment AD, noting that AC now must be congruent to CD, turns out we can see here that AC is congruent to DC, and that's going to be denoted in the steps here in a moment. But we should also note in the picture, really I would argue now, is that we have a side that's shared by the two triangles in question, and that side is simply side BC. And as we've seen in the past in a prior section, we can argue that BC is congruent to itself by something called the reflexive property. All right, the first thing we note here again is the given. As a matter of fact, the first two steps are given. But then we see here that AC is congruent to DC, which again I've already denoted in the picture. And if, in fact, as far as the reason goes, it's as simple as the midpoint theorem. Then you can see here in step 4, I've denoted that BC is congruent to itself. Noting again the reason, as I noted again earlier, reflexive property, or the reflexive property of congruence, which is just as effective if you note that. If you don't, if you just say reflexive property, that should be okay. Triangle ABC therefore is congruent to triangle DBC, and notice the order A, B, C is congruent to D, B, C. In that order, that's what we're going to note. And the reason they're congruent is by side, side, side. So in the context of the statements, we've got a side. AB is congruent to DB, another side. AC is congruent to DC, and yet a third side. So side, side, side congruence, or the side, side, side postulate. Continuing on. So we're going to go ahead and write our own kind of two-column proof for both of these questions. So let's take a look. So we have two triangles. We have triangle ABC and we have triangle XYZ. That's what we're trying to prove technically, in that we can see here we're trying to get them to be congruent. Given the fact that AB is congruent to XY, which you can see also the markings for, AC is congruent to XZ. Again, the markings are shown accordingly. And then BC is congruent to YZ. So let's prove this. First thing I'd like you to do is highlight, of course, your two columns, one with statements, one with reasons, as the column and headings, that is. And as you can see, hopefully right away, as we typically like to do, we highlight all the givens. Okay, so all your givens are denoted as such, wherein we see AB again congruent to XY, AC congruent to XZ, and BC congruent to YZ. As we've said earlier, right, in the last proof, we've got side, side, side. So that in and of itself should be enough to justify that yes, triangle ABC is congruent to triangle XYZ, and the reason is the side, side, side postulate. Next example, we're trying to prove triangles congruent in that order, so careful with R, ST, that must be congruent to UTS. That's what we're trying to prove. RS is congruent to UT, and yes, they're marked accordingly. RT is congruent to US, And the other part that you need to mark, even though it's not denoted in the given, is that TS or ST, same thing, is congruent to itself. Like we saw back on step 4 from the example, this will be an important part to the process. So let's see how this unfolds. Yet again, highlight your 2 columns, statements and reasons, as your column headings. Your givens, there's 1, there's 2, so you've got side, side, and then you can denote, of course, that the reflexive property, noting that ST is congruent to TS. If you flip the letters, that's acceptable. I would be okay with that. But ST congruent to TS, again, because of the reflexive property. So now we can highlight again S, 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 and if it isn't already obvious, we can denote that our 2 triangles are congruent. Triangle RST is congruent to UTS in that order by side, side, side. Let's move on to the next page. The side angle side postulate is another way to show that 2 triangles are congruent. And it is used, the side angle side postulate. Another way to show that is to use this. So if 2 sides and the included angle of one triangle are congruent to 2 sides and the included angle of another triangle, then the triangles are congruent. So for example, it says for each diagram, determine which pairs of triangles can be proved congruent by a side angle side. So as we take a look here, we've got 2 triangles. We've got angle B congruent to angle X. We've got AB congruent to XY, and we've got AC congruent to XZ. Now the word included is a particularly important word in the context of what we're doing here. The included angle speaks to an angle that is literally between 2 sides. In this picture, angle X is included between this side XY and this side XZ. However, on this picture, angle B is not included. So that's a problem. In triangle ABC, the angle is not included by the sides AB and AC. So the triangles cannot be proved congruent by side angle side. Quite literally, it's called side angle side with A in the middle because you've got one side like we see here, another side like we see here, and the angle included in between. But again, these 2 are not congruent because, well, angle A is not included. What about part B though? Part B, you've got triangle DFE, and you've got triangle JHG. Or if you go in the other order as they describe here in a moment, you'll see DEF and JGH. That order technically is acceptable as well. If you start with D and then go to E, of course, F would be your third, and then those letters as well, JGH. Anyways, this side is congruent to that side. This angle is congruent to that angle. And then lastly, this side is congruent to that side. So side, angle, side. Again, angle in the middle. Side, angle, side. Again, angle in the middle. The right angles are congruent and they are included angles, the included angles for the congruent sides. Therefore, triangle DEF is congruent to JGH by side angle side. Part C. We can see here where the lines here and here are segments PQ technically and SR are parallel. Because they're parallel, we'll be able to make a connection to this angle being congruent to that angle by virtue of alternate interior angles. Since the lines are parallel, alternate interior angles are congruent. The included angles, therefore, angle 1 and angle 2 are congruent, like I said, because they are alternate interior angles for 2 parallel lines. Angle 1 is included between those 2 sides. Angle 2 is included between those 2 sides. So side, angle, side, side, angle, side. And notice side PR is shared by both triangles. So the reflexive property may be used at some point or another when this type of thing unfolds. In this case, you're only highlighting side, angle, side because you're already told that PR is congruent to itself. But PR is congruent to itself again by virtue of the reflexive property. Anyways, triangle PSR is congruent to RQP by, again, side, angle, side. Okay, so we're going to go ahead and continue. Got a couple of proofs to take a look at. For number 1, write a two-column proof if NP is equal to PM, NP is perpendicular to PL, and triangle NPL is congruent to triangle MPL as our proof statement. Our proof statement is to, again, say that these two triangles here and here are congruent to each other. Statements and reasons set up, given, as you can see. So let's go ahead and continue. And by the way, before I do this, let's note that we've got a side that's congruent to itself. Why not kind of get that set up? Using the reflexive property again, we can make that denotation. Continuing. Angle MPL is a right angle by perpendicular lines, forming right angles, but also angle NPL. So again, perpendicularity should help us then understand that we do have right angles, and you do have to make that statement so that you could say they're of course congruent, which they say in the next step. Angle MPL, this angle right here, is congruent to NPL, this angle right there. Okay? All right angles are congruent is your reason for that. Step 4, as I already discussed in our depiction and as I denoted, PL is equal to PL. I'm not using congruency here, but technically an equal sign is sufficient for our purposes, distinguishing congruent, or sides that are equal in length. Reflexive property of congruency technically is what they depict it as, interestingly enough. And then lastly, we've got our final statement, which is of course triangle NPL is congruent to triangle MPL by side, angle, side. And yes, the angle is included. So here's your angle portion of that. Here's your side portion of that, and here's your other side portion. So side, angle, side. All right, second proof in this little category of exercises. So we've got a two-column proof again to distinguish. We're told or given that AB is equal to CD. AB is parallel to CD, therefore prove that triangle ACD is congruent to triangle CAB. So ACD is congruent, hopefully, to CAB, which I think we might have to adjust. So if it's the way I'm reading this, I'm probably going to go, instead of with CAB, we'll say again ACD, so DBA. Okay, that's going to make more sense in context. And as far as what we've seen in a similar situation up in the above part C example, two parallel lines will dictate that we, in this particular case, like that example, we have alternate interior angles congruent. So we know we have that, and we can also argue for reflexive property application where AD is congruent to itself. So again, we're going to try to prove that ACD is congruent to DBA. And by the way, as I've denoted in the past on various congruency problems, C and B are the second letters for the sake of maybe just noting that those two angles have to be corresponding but congruent. Okay, there is a shared side of which AD you see here, but in the letters you see A and D, first and third, and first and third on the other triangle, D and A, kind of flip-flopped. So I think it's pretty obvious that we are in fact going to prove by side, angle, side that the two triangles are congruent. Again, side, angle, side. We just had to set ourselves up for it, make that correction, of course, in the proof statement. Statements and reasons set up. There's your first step, you're given. Your alternate interior angles theorem, noting that is congruent to that. Angle BAC is congruent to DCA. Alternate interior angles theorem, thanks to the parallel lines. AC is congruent or equal to itself by the reflexive property. And then last but not least, the two triangles are in fact congruent. And yes, this is DBA. But again, these two triangles are congruent by side, angle, side.